Okay, today our lesson is on reflection of light. Now in here, I'm going to go through with the answer with the PDF file here. The reason for that is because after the written text, there's a lot of drawings. And in order to draw the straight lines, it's easiest if you look at the PDF file. So in here, let's take a look at the first part. Now, so in here you see that the first part, there's a lot of light is coming out. So you see in here. So you can see in here, the lines here are all going from the left to right in the parallel. That's why in here, the first drawing here is the first part here is the parallel ways. And then the second one here is diverted ways. The reason for that is because the ways, as you can tell, is going outward. It doesn't converge. Compared to the parallel lines, it's going straight, but yet it's going further and further away. And some of you might not be able to read what that is, so let me just type it in here. It is divergent. So in here is the diverted way. That's how you spell it. Okay? It's diverted ways. And then the next to it, you see that all of them are converting into the point. So in here, you see this. So you see here, all of them are converting to one point. And here, we give a name of convergent. 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 So in here, we got divergent and convergent. Convergent means that it will come to one point. That's why we call it converge. And for the divergent point, it means going away. It will not come to the same point, so we call it divergent. And the last one, in here you see that over here, this one is going away as well. So in here we use this as the divergent weight as well. So that's why in here we call it divergence. Okay? So in here, the first one is parallel, second one is divergent, number 3 is converge, and the last one is diverge. Now in here, if we carry on looking at the luminous and non-luminous object. Luminous means that something you can see, and the objects that can emit their own light so that you can see it. So in here, some example. You've got the sun, the candle, and the light bulb. Okay? So I assume you know how to spell light bulbs. It's LIGHT-BULB. So it's the light bulb, the last one there. And for the non-luminous objects that cannot emit their own light, the bulb, the moon, and even got a dolphin there, all those are non-luminous because it will not emit light. Now, in here, why can we see things? And here, we can see things only if the light enters our eyes. The easiest way to test it is if you close your eyes, the light cannot go into your eyes, so that you cannot see the object. Even with the light out there, as long as there's no light entering into your eye, you will not see anything. So in here, in darkness, there will be no light at all entering into our eyes, so that you cannot see anything at all. Now, next part here is, you see that the light wave is going from the object, the candle there, enter into our eyes. So that's why you see the arrow is starting from the candle itself and is coming from the candle and entering into the person's eye. Now, seeing non-luminous objects. So since that is non-luminous, it will not give out light. What will happen? The light refracted from the non-luminous objects enter our eyes. So if you look at the diagram, the sunlight is shining on the apple and is reflecting off the skin of the apple, and then it will reflecting off and enter our eyes. That's why we can see an object, because it's refracted from a non-luminous object in order for us to see it. If there's no light, it will not reflect at all. With the light, it will first hit the object first and then reflecting, entering into our eyes. So at the bottom of page 1, we have the waves entering our eyes from objects. So in here, let's take a look at the first one. From near objects, you will see that it's a divergence wave because an object there is going away into our eyes. It doesn't come to one point. So in here, this one, again, we will call it divergence. D-I-V-E-R-G-E-N-T, divergent. So in here, that's what we call it, a divergence wave. That's the first object from the near object. We'll give it as a divergent object. And then from the far object here, you see that it's going from the very far away and it's entering our eyes. The wave itself is longer, and yet it will have the same characteristic as the last one, but it's longer, that's all. So in here, we also use the name divergent. So in here, we also name this as a divergent wave because you can see the objects are from the very far away entering our eyes. And yet, the only difference between the near object and the far object is the distance. It's longer it is. Now, compare these two, the near and far object, to the last one. In here is the distant object. In here, the distant object, you see the lines are going parallel. It will go in with the parallel lines going into our eyes. That's why in here you will be able to see that it will enter our eyes as it is. So that's why we call it parallel lines. And in here, we use the word parallel wave. Okay? So in here, that's the first page, and let's go over to the second page. Now, in the second page, as you can tell, there's some of the drawings that you need to label. For example, there's the wave box, that is the source of light, is going, starting from, and is entering our eyes. So in here, if you look at it, the lights coming in, we give it a name of calling it an incident wave. So in here, let me just write better so you can see that it's called incident wave. Okay, so in here we call it incident wave. For the one is starting from your left hand side there, it's going in at an angle. So in here we call it the incident angle. Now, in here in the middle, you will see that there's a dotted line. And all of you by now should know it in Form 3, we call that the normal. Okay, so in here, the middle line, the dotted line, we call it normal. So in here, you see that it is 90 degrees to the mirror. The mirror at the bottom there, you see that it will reflect the light from the wave box here going out the other side. And from your right hand side, you will see that we got the refracted rays and the refracted angle. So just let me make sure all of you know how to spell that by writing it down. Okay, so in here, your left-hand side, everything is called the incident. You got the incident weight, incident angles, and the middle you have the normal, and then after that, on your right-hand side, you got the refracted weight and refracted angle. And we will talk about what is the property of the incident angle and the refracted angle. It is related to normal. We will give it how to talk about that in a second. So let's talk about what you have learned in Form 3 first. In Form 3 mathematics, you have learned about something called normal. And in here, one particular word you need to know is called perpendicular. In here, this word, let me spell it out so that it's easier for you to see it. It's P-E-R-P-E-N-D-I-C-U-L-A-R. It's called perpendicular. Okay? So in here, perpendicular means that it is 90 degrees. So from the mirror up, it is 90 degrees. We call that perpendicular line. And from that, the angle of incidence, we give it the letter I because incidence starts with the letter I, so we call it I. It's the angle between the normal and the incident weight. So in here, it's between the normal line, the dotted line, and the weight box. And that angle, we call it incident angle or the angle of incidence. And the other one is the angle of refraction, R. So in here, you see that next to normal, there's a refracted angle, okay? So it's important to know that which line is a normal line, because in this diagram, it's easy to see that the dotted line is the normal line, but from now on, a lot of the lines will be more difficult to see what it looks like. So in here, make sure you know the one we're coming in, we give it the letter I, and the one refracted, we give it the letter R to indicate that it's called the refracted angle or the angle of refraction. Now, in here, the next part, we draw the normal on the surface, and in particular, it's a curved surface. So in here, you have to be careful. Now, remember in a circle, if it's 90 degree normal, we start from the center and we come all the way across as in the diameter. Okay, so it come out and keep on dotting it to give it the dotted line. So please draw this in with the dotted line, and on the bottom part is the incident weight I because the light is coming in, and the R coming off is the refraction, the refracted ray. So in here, I and R should be the same. So please make sure you measure the angle. You need to measure this accurately because in here, if you don't have a protractor, you will be in trouble with this chapter because all the angles coming in will need a protractor, okay? So please measure it off and see what you get from the angle, okay? So that's the first diagram. Now, in here, the second diagram, you will see that you need to draw in the normal first, the dotted line. Normal is 90 degrees to the surface. So in here, you need to measure 90 degrees from the surface, and it helps if you draw a line perpendicular to the surface of the circle. So in here, you see that if you have the dotted line, then you have the I, the angle of incidence, and from that, it has an R, the refracted angle, R coming off. So in here, you need I and R for this drawing to work. And right now, all you need to know is I and R are the same. The angle coming in is equal to the angle coming off of it, the refracted off of it. So in here, that's what we have for the law of refraction. If you refer to your textbook, page 8, that is the law of refraction. Now, in here, the incident weight, the refracted weight, and the normal are all lying in the same plane. Well, actually it's on the same plane because it's grammar. But in here, physics, we don't talk about that too much, so it's lying in the same plane is fine. Now, but the second law is important. You need to know this. The angle of refraction is equal to the angle of incidence. This is important. You need to know this one. So for this one, make sure you know that this is important. You need to know this one. Number 2, the angle of refraction is equal to the angle of incidence. You need to remember that. Because from all the drawing here, if you don't know how to draw this, it will be more difficult to see what it is about. So please make sure you can draw that, okay? Now, in here, let's take a look at page 2, the bottom part on the first example. Now, in here, you will take a look. If you take a look at the example 1 here, a light wave is incident on the mirror as shown. So in here we got the incident wave from the wave box coming in at the angle of 62. But remember, this 62 is not the incident angle. It's 62 at the bottom. And what we need to do first is draw the normal in first. If you draw the normal in first, you will see that we got 90 degrees. And just let me write down. So we got that we need to find out what's the incident rate, I. It will be equals to 90 degree minus 62 degrees. And that would give you 28 degrees, okay? So in here, make sure you know how to get this one, how to get the incident, the angle of incidence or the incident angle, which is 28 degree, as shown you in this drawing, the I. So from that, you got the I is equal to 28 degree, and then from that, you need to measure another 28 degree to the top, and that we'll call that R. And that's how we're going to get the first part A. We got the I, and the R here is also equal to 28. So in here, let me just add on to this by saying, in here, R would be equal to 28 degrees as well. Okay? So in here, you can tell that the way of incident, I is equal to 28 degree, and R is equal to 28 degree. That's how we get this, by drawing in normal. Again, I can't emphasize how important it is to draw in the normal first. As the first step, you need to have the normal. If you don't draw in the normal, you will get into trouble really soon, as I will show you in the next example, example 2. Now, in here, in example 2, a horizontal light wave is incident at the plane mirror, which makes an angle of 30 degrees with the horizontal. So you know that from your drawing, from the drawing given, 30 degrees at the bottom. So you need to move it upward, move all the way to the top part to give you 30 degrees at the top. So you know that that 30 degree is the one between the light wave and the mirror. Now, the first step, as I mentioned in the last example, is to draw in normal, the dotted line. So in here, if you draw in the normal, you will see the dotted line first, and then you will be able to start to work your way around it. So in here, after you get the 30 degree, and what is the one in between there? So we need to look at the way of incident. And in here, let's see if I can put it somewhere it's not next to the drawing. So in here, we need to find out what is the incident way. And in here, it will be equals to 90 degree minus 30 degree, because the one that's coming in is at the top, right? So in here, we got the answer, that is 60 degree, okay? So in here, that's how we get the first part. So in here, that's how we get the incident way. That is equal to 60 degrees. And if we measure off 60 degree, and then we can start from the normal, going downward 60 degree. Because if you have the way of incident that is 60 degree, you will also get the way of refraction, which is 60 degree, which is the same. So in here, make sure it does not look like a 90 degree angle here. Actually, if you add it up, 60 plus 60 is 120. 120 plus 30 is 150. So it does not look like 90 degree there. Please make sure you know that. When you draw in, use a protractor. Make sure the angles are correct, okay? Because if you didn't draw it correctly, the next two questions, you will see that it will be even more challenging to see what that is about. Now, please give a second, draw in, make sure you know what it looks like, okay? So in here, it's not difficult, these first two examples. Now, in here, number 3, it's getting a little bit more challenging because, as you can tell, the drawing itself actually is getting to be a lot more lines going to get involved in, okay? So in here, number 3, we only know that the lights go in from your right hand side to the first mirror on top is 50 degree. So in here, if you know that the top part is 50, and please draw in the normal now with the dotted line, and I will show you the really simple calculation. The incident way again, we got that equals to 90 degree minus 50, the one given in the question. That would equal to 40 degrees. Okay, so in here we know that it's equal to 40 degrees. So after 50, and please draw in the normal line of the dotted line, and then you can write down that is 40 degree as the incident weight, I. And from the law of refraction, we know that R would be equal to I, which is 40 degree again. So you can compute the first refraction of R, that is 40 degree. Now, after that, that is only the first part. But when the 40 degree, when the reflected light 40 degree coming off the top mirror, it will hit the second mirror, which is in the vertical line. Now you have to be careful. We got the 40 degrees at top and the 40 degree next to the mirror. And from that, we come to a relationship of alternate angle. Remember in Form 1, you learn about that. So in here, let me just remind you of the alternate angle. ALT, alternate angle here. Okay? So in here, from the triangle's property, alternate angle, you see that 40 degree, and then you need to draw in the normal line again now with the dotted line. From that, we will be able to calculate what is R. So in here, it's really simple. R will be equals to 90 degree minus 40 degree, and it will give you 50 degree. So in here, you see that that's how we get that refraction rate, the second refracted rate of 50 degree. as the incident weight is equal to 50, and then I, the refracted weight, is also the incident weight, and the refracted weight R, both of them are 50. So that's how we get this 50 degree. And please draw this line in, so you will see that how it's reflecting off two mirror, how it works with the refracted weight. Now, number 4 is a little bit challenging in terms of drawing because it's limited by the space you have. So please bear with me to go through the step one by one. So please ignore the top part. Just look at 45 degree entering into the light weight, okay? So in here, we got 45 degrees in. So in here, that would be easy. The first one, we just say that, oh, I would be equals to 90 degree minus 45 degree, which will give you 45 degree. So that's how we get the first incident weight. When it's coming in, it's coming in at a 45 degree angle to the normal. So make sure you draw the dotted line in now and draw the first 45 degree angle next to your way of incidence, the incidence way. So next to that, we got the R is also 45 degree. So it will go 45 degree going to the top. So in here, it just so happen, it does not have to be, but only in this case, 45 degree plus 45 degrees inside is 90 degrees. So inside there, we got 90 degree. Going up, that is the incident weight. Now, in here, it comes to a math problem for you. Okay? So in here, we got a 90 degree inside, and then it's going on top, going to the top. But you don't know what angle that is yet. You do not know that yet. But we know that we can write a normal line, the dotted line in first. Okay? So in here, what we could tell you is 45 degree plus 45 degree plus 45 degree. So if you work out the math, it's not that difficult. So in here we see that there is a triangle formed at the corner there. So what we need to do is, by looking at that triangle, okay? So in here, you can tell that, oh, it's the way of incidence now is coming in, and we know that it's coming in a deep angle because we got 90 degrees in the middle there going up. So from that, we can take a look at what we got. Now, so from here, you need to know that all these angles, they would have a normal of 90 degree again. So on the top, you will need to draw in a dotted line. And from that dotted line, you can measure it. And it will give you 15 degrees. From the one we're going in, and the one coming in, and the next one. And that's why we see that at the top there, we got 15 degrees as the incident weight. Now, in here, you need to be careful. You see the angle there, 75 degree. How do we get that 75 degree? It's by doing the math here first. So let me write next to it so you can see it. So in here, the top corner there, we got 180 degrees. It's minus 60 degree at the corner. But how about the corner next to it? So you see the bottom part, it should be 45 degree. And what do we get? that would give you 75 degrees. That's how we get the 75 on top. So in here, once you get the 75 on top, you will know that, oh, okay, the incident wave would be equal to, that incident wave would be equal to 90 degrees minus 75 degrees, which will give you 15 degrees. So that's how we get the wave of incident at the top. That is coming in at the angle of 15 degrees. So from that, we can say that, oh, okay, the top part is 15, and then next to it, the refracted angle would also be 15 degrees. Okay? So in here, that's what it looks like. Okay? So from the top, again, let's go through it one step at a time. So from the bottom part, the light wave is coming in at 45 degree angle, and then you work it out to be the incident wave just so happen be 45 degrees as well. 45, 45, and then the refracted wave will be 45. From that, it's going up, but we don't know what angle that is yet. So we look at the triangle it formed at the corner there. We got 60 degrees at one corner. And then what happened to the bottom part? What is the remaining angle for this triangle? It's 180 degrees minus 145 degrees, 45 degrees, 45 degrees to give you that 45 degrees at the bottom part. Okay? So in here, that's why the bottom part is 45. And we got 180 minus 60 minus 45 to give you 75 at the top. From that, we can say that, oh, okay, the normal is 90 degrees minus that 75 to give you the incident wave of 15 degrees. And from 15 degrees, you can draw in the other one as well to give you the final answer of 15 degrees coming out of the top of the mirror. Now, in here, the bottom part, we will not discuss this at this moment. And for this topic, the refractor of light, we will talk about that in the third lesson. I will come back to this later on. So this part, after you finish this, we will be taking a look at page 4. Okay? So in here, in page 4, you will see that there are a lot of drawings you need to do. That's one reason why I need to draw in this answer first, because if you draw it by freehand, you will not be able to get the answer at all. So I will supplement the spelling in case you didn't see it clearly. Now, in here, the top part, the regular refractions on a smooth surface. So you see that you need to draw the normal in, and the light will be coming off it, nice and parallel. Compare that to the diffuse refraction. So in here, if you take a look at it, the top part is nice and smooth, but the joint next to it, let's assume the first drawing is 10 degrees, and next to it 10 degrees is 20 degrees. It will be bouncing off to different angles already. And the next one is, the second one is 40 degrees. So in C, 40 plus 40 is 80. So inside there, it will be 80 degrees going off long way already. And then next to that, there's a 20 degrees. So in here, 20 plus 20 is only 40. So you see it's bouncing off in all different angles. That's why you see that, oh, okay, all of them will be different coming off of the diffuse refraction. Now, the next part. So let's take a look at the next part. In here, on a regular refraction, is occurring on a smooth flat surface. So there's no rough surface as we have seen on the top there. It's diffusing the light in a different angle. So in here, we've got a mirror or calm water would give you that nice and smooth flat surface. And anything else, the board, chalkboard, you name it, everything would have a rough surface. So in here, we compare the image. The image in the regular refraction is nice and clear, but the other one is not clear at all. It's no clear image can be found. Now, so in here, the explanation. the regular refractions, because all the waves are going in parallel, that's why the angle of incidence are equal for the incident wave. So all the reflections are equal because all of them are coming in the same angle, all of them coming out at the same angle as well. So in here, all the reflected waves are in parallel. Now, compare that to the diffuse refraction. Because all of them are coming in at different angles, the incidence wave, all of them are coming in different angles. That's why the angles of refraction, all of them will be different. All of them are different. That's why you cannot see one clear image. And it results in the reflected waves are not parallel because you cannot see it. So in here, the first one and the second one, do they obey the law of refraction? Yes, for both of them. Because the first one and the second one, all of them will be reflecting the same way as before. And now let me finish off with the last example here as the last example of this lesson. Now in here, the words is a little bit hard to read. It says, figure 8 shows a playground after raining. So in here, you can barely see it. The diagram is a playground with the reflection on it. Image can be seen on the calm water surface on the wet ground. Now in here, only answer A. Explain why images can be seen on the calm water surface. So in here, we need to use the terms we have seen on top. The calm water surface is smooth and flat. The regular reflection occurs. Therefore, here image can be found. Okay, so in case you cannot see these wordings, let me just write in here so you can see what it says. Calm water surface is smooth and flat. From that, regular reflection occurs. Okay, so let me see, we can move it up a little bit. Okay, so you can see what is reads. Okay, so in here, make sure you know that some of the keywords have used on the above summary. It's a nice and smooth and flat surface, and the regular reflection occurs. Okay, some of these words you need to use, and as a result, clear image can be formed. That's the reason for that. Okay, so that's the end of the first lesson on the reflection of light.